You might have noticed that so far everything that we've talked about has been about functions that are positive, functions that are living above the x-axis. So now we want to answer the question of what happens when we're talking about areas of functions that go below the horizontal axis. What kind of picture should we have in our mind, and how should we actually go about doing these computations? So example 2 is asking us use a left Riemann sum with 4 rectangles to approximate this integral from 0 to 4 of minus x dx. So the first thing that we can think about is having a picture in our heads. And the function minus x, well, that's a linear function, slope minus 1, y-intercept equal to 0, so its graph looks something like this. Since we're taking the integral from 0 to 4, we care about 0 here, and we care about 4 over here. And since this function lies below the x-axis, we actually can't really use our geometric picture really to help us very much when we're doing this area approximation. So instead what we're going to do is we're going to use our algebraic approach to Riemann sums, which is to use a little formula that we have. So if we're working with our integrand here, being the function minus x, then our Riemann sum with 4 rectangles says take the sum from I equals 1 to 4, since we have 4 rectangles, of f of the left Riemann sum says use the index I minus 1 here, times delta x. So we have a couple questions, which is what exactly are the xi's, and what is delta x here? So delta x, we know this means since we're doing 4 rectangles, we need to split up our interval from 0 to 4 into 4 different pieces. So we want to think about the entire length of the rectangle, or the entire length of the interval, which is 4 minus 0, divided by the number of rectangles that we have, which is 4. And so our delta x here is 1. Our xi's come from us splitting up this interval into different pieces. So we have x0 at the left end point. Then we're adding x1, x2, x3, and x4 here according to kind of splitting this interval up into equal pieces. And the way that we split this up into equal pieces is we have all of these x values at actually the integers. So x0 is at 0, x1 is at 1, x2 is at 2, x3 is at 3, and x4 is at 4. So when we're adding all of these pieces up here, we need to think about first starting with I equals 1. So if we substitute I equals 1 into this sum here, we're looking at f of x0 times delta x plus f of x1, since we increment I by 1 now, times delta x plus f of x2 times delta x. We stop when I equals 4, which is when the index on our x value is 3. So the last one that we're considering here is f of x3 times delta x. Now we know what all of these xi's are, and we know what delta x is. So this is going to be x0 is 0, delta x is 1, x1 is 1, delta x is 1, x2 is 2, delta x is 1, and x3 is 3, and delta x is still 1. So multiplying by 1 doesn't do anything, so we can just compute f of 0. F of x is minus x, so this is going to be minus 0, which is 0, plus f of 1, f of x is again minus x, so we're adding minus 1 there. F of 2 is minus 2, f of 3 is minus 3, and this leaves us with a good minus 6 as an answer. So the first thing that we're noticing here is that our Riemann sum is telling us that what we need to do is we need to take negative areas for when we're looking under the axis here. So this Riemann sum, or this integral, should be approximately minus 6. It's not going to be exactly minus 6, but certainly it's going to be negative no matter what it ends up being. So geometrically, what exactly are the rectangles that we are computing here? Well, we said our rectangles have width area 1, or have width 1. And so we're taking this interval from 0 to 4, and we're again kind of splitting it up into these 4 pieces here. And the height of each rectangle is determined, again, by f of the left endpoint, since we're doing a left approximation here. And so the rectangles that we're thinking about here, well, this this first rectangle has height 0. This second rectangle here, we're using height -1, meaning that what we can do is we can think about that as being the rectangle here, which lies between the curve and the axis. And we're thinking about this rectangle as having a negative area since it lies below the axis. The third rectangle has height -2, which lives here. So we're thinking about the third rectangle as again being a little bit taller, but again having more negative area. And the last rectangle has height -3. So when we found this approximation of -6, what we did was we took up the areas of all of these rectangles and we made them negative because they all were below the axis. So negative areas are going to be okay for us. And that, in fact, is going to be the conclusion here, which is going to be that area below the x-axis counts as negative. Maybe that seems a little bit weird, but it is going to mean that the integral has much nicer properties than if we counted that area as positive. So let's do an example here where we're actually looking at some of these negative areas. So we're asked to compute the integral from -2 to 3 of f of x dx, where f of x is this piecewise function. So in order to actually do this integral, we're going to want to think about what does the graph of this look like. But between the x values of -2 and 0, f of x is this function x plus 3. We know that is a line with slope 1. At -2, we're going to have an output value of 1. At 0, we're going to have an output value of 3. And so we have the straight line there. Sorry, that line isn't terribly straight. Between the x values of 0 and 1, we have that our function looks like the line -5x plus 3. And the line -5x plus 3 has slope -5, y-intercept 3, so it's going to pass through this point. And at x equals 1, we're going to have y being -2. So we're going to have the straight line passing through these 2 points. And the last section that we're looking at here are the x values between 1 and 3. Our y value is -2, and in fact it's always -2, so we have a constant function here off to the right. Great. So we have the graph of our function here, and we want to think about actually doing the integral here, which means that we need to get a picture of what the area under the curve looks like. So under here, I'm using a little bit loosely because some of the area that we're going to be computing is above the curve. More properly, we should be using the language area between the curve and the x-axis, and that's the picture that you really want to have in mind, especially when we have functions that have negative y values here. So let's go ahead and think about some of the different pieces that we have when we are computing this integral. We want to split this up into triangles and rectangles here because those are shapes that we know how to compute areas of. Certainly we don't have any circles to worry about here, so we're not too concerned there. So I'm seeing a bunch of different triangles and rectangles here. So let's maybe think about this triangle here. We're also going to have this rectangle. We're going to have this triangle. Oops, sorry. We are going to have this triangle. since we're thinking about area between the curve and the x-axis. And last, we are going to have this rectangle. Great. So the sums of all of these areas that you see here, where we're counting the green and red areas as negative, is going to be this total integral, since it's the area between the curve and the axis. So we want to start off with these different pieces here. We can call the black area A1. And A1 is going to be, since it's a triangle, it's going to have area 1/2 base times height. So its base length here is 2. Its height is also 2, and so its area is 1/2 times 2 times 2, which works out to be 2. Great. Our blue area here, which maybe we can call A2, is going to be, it's a rectangle, so its area is just base times height. Its base length is 2, and its height is 1, so its area is also 2. Moving on, we want to think about what our purple area is here. Maybe we can call this A3. But we have a little problem, which is that we don't exactly know what its base length is right now. But we know that it goes from 0 to whatever this x value is, and maybe we should spend some time figuring out what that x value is. We know that the straight line here between 0 and 1 is given by the equation minus 5x plus 3. So we want to find out at what x value does minus 5x plus 3 hit 0. So a quick calculation. Oh, that's a terrible 5. Minus 5x plus 3 equals 0. This occurs when 3 equals 5x, which is to say that 3/5 equals x. So we know then that the base of this rectangle is 3/5. So our area is going to be 1/2 times 3/5 times the height of that triangle. And the height of that triangle is going to be 3. So actually doing this computation, it looks like we have 9/10 here. Continuing on, we're going to have some green area here. So area 4 we are on. The base length of this rectangle, well, let's see. If we had a length of 3/5 there, and we need to get up to 1, the x value of 1, then the base length of this rectangle is going to be 2/5. So this is going to be 1/2 times 2/5 times its height is going to be minus 2 here. So we're going to think about the fact that it is below the axis as meaning that it's got a negative height. And so times minus 2. And it looks like we are going to have here, this area is minus 2/5. For the purposes of getting a better decimal later, we're going to write this as minus 2/10, or as minus 4/10. Last but not least, we have the red rectangle, which is going to have base length 2 and height minus 2, which is going to get me an area of minus 4 for my red rectangle. So putting all of the pieces together here means that when we're doing this integral computation from minus 2 to 3 of f of x dx, we need to add up all of these rectangles. So we have A1 plus A2 plus A3 plus A4 plus A5. And adding up all of these numbers, we'll have 2 and 2 is 4. 9/10 minus 4/10 is going to be 5/10. So we have 4.5 so far. Minus 4 is going to give me exactly 0.5. So here we can again kind of take advantage of the geometry of the situation, the fact that we know how to compute areas of triangles and rectangles, and we can find this area between the curve and the x-axis using the fact that area below the axis is negative, and we are able to compute this integral here.